Hi and welcome back. In order to analyze different types of structures, we have different methods. One of these methods is called moment distribution method. In today's video, we will draw the moment diagram of an indeterminate beam using moment distribution method. As you can see in this figure here, we are going to draw the bending moment diagram of this indeterminate beam. The beam is fixed at support A and support D. The B and C supports are rollers. There is a 20 kN per meter uniformly distributed load from point B to point C. And in the middle of point C and D, there is a 250 kN point load as well. In order to perform moment distribution method, the first thing is to calculate the fixed end moments. Then we are going to find the stiffness factors, and then we are going to find the distribution factors. So in the first stage here, we are going to calculate the fixed end moments. As you might see in here, from point A up to point B, there are no loads. So the fixed end moment from point A to B will be 0, and the fixed end moment from point B to C will be 0 as well. But since we have a uniformly distributed load from point B to C, the fixed end moment formula will be W times L squared divided by 12. The clockwise direction for the moment will be assumed as positive. And for the point load here, the fixed end moment formula will be P times L divided by 8. So let's obtain these moments. The fixed end moment from point B to C will be minus WL squared divided by 12, which is going to be minus 20 times 12 squared divided by 12, which will be minus 240 kilonewton meters. From point C to B, this value will be positive. It will be 240 kilonewton meters. So let's find out the fixed end moment from point C to B. From point C to D, for the point load, the fixed end moment will be P times L divided by 8. So this will be minus 250 from point C to D, and it will be 250 from point D to C. Once the fixed end moments are calculated, the next thing is to calculate the stiffness factors, or K. The general formula for obtaining the stiffness factor is 4 times modulus of elasticity times moment of inertia divided by L, or length of the member. EI is going to be assumed as constant for all the elements of the structure. In here, the stiffness of element AB will be 4 times E times I divided by 12, which is the length of the element. From B to C, it will be 4EI divided by 12 as well, since the length of element BC was 12 as well. And for the last element, which is CD, the stiffness factor will be 4EI divided by 8, since its length was 8. Once we have the stiffness factors, in the third step we are going to calculate the distribution factors of the structure. The general formula for obtaining the distribution factor of the element will be stiffness of the element itself divided by summation of the stiffness of the elements meeting at the joint. A and D are rigid supports in this example, so their stiffness will be infinite, and the distribution factors at those joints will be 0. From B to A, as we know, the stiffness factor was 4EI divided by 12 for the element AB, and the total stiffness factors of the elements meeting at joint B is given as this. If we simplify this, we will obtain 0.5. This will be same to the distribution factor from point B to C. From point C to B, the distribution factor will be calculated as follows. If we simplify these values, the total distribution factor will be 0.4. From point C to D, the distribution factor will be given using this formula. If we simplify this, it will be given as 0.6. As I mentioned earlier, at points A and D, since they are rigid, the distribution factors will be 0. Now we are going to perform the moment distribution method step by step and obtain the final moments at the joints. So in here we have the joint names, and besides that we have the members which are meeting at that specific joint. As you can see, at joint A we only have member AB, while at joint B we have members BA and BC, and so on. Next thing is to write down the distribution factors below each of the members. And next, we will write down the fixed end moments. From A to B, we have no moment since there was no load. At joint B, we have a negative minus 240 kilonewton times meter moment. In order to balance this moment, we have to have the same amount of moment with a different sign at the same point. So in here, we will write down a 240 kilonewton times meter of positive moment. That positive moment will be distributed between members BC and BA based on these distribution factors. So if you multiply 240 into 0.5, it will be 120 in here and 120 in here, since this is 0.5 as well. From point C to B, we had the fixed end moment as 240, and from point C to D, we had the fixed moment as minus 250. If we add both of these moments, it will be minus 10. The balancing moment in here will be plus 10. That plus 10 will be distributed based on these factors. So 10 times 0.6 will be 6, and 10 times 0.4 will be 4. And at point D, we had a fixed end moment of 250. Since this is a fixed support, the distribution factor is 0. 250 times 0 will be 0. Same applies for here, but since we have no moment in here, we haven't written down anything in here. Now we are going to carry over these moments from one joint to another. To the fixed support in here, the carryover factor will be 0.5, which means that half of this moment will be carried to this joint. Half of this moment will go to joint C, which will be 60. And half of this moment will come to joint B, which will be 2. This will be multiplied by 1.2, and 3 kilonewton times meter will go into here. As I mentioned earlier, this value will be multiplied into 0, and there will be no moment to be carried over to this side. Now again, we will balance these moments at the joints. This will be multiplied by 0, and no moment will remain. This will be multiplied by 0, and no moment will remain. At joints B and C, as you can see, we have 2 and we have 60 in here. The balancing moment for this 2 will be minus 2. The minus 2 moment will be distributed based on these two factors. 2 times 0.5 will be minus 1, and minus 2 times 0.5 will be minus 1 in here. This moment, however, will be distributed based on these factors. The balancing moment will be minus 60, minus 36 of which will go to CD, and minus 24 will go to CB, based on the distribution factors. Again, we will perform the carryover. In here again, as you can see, this minus 1 will be multiplied into 0.5, and minus 0.5 will come to this joint. Minus 24 will be multiplied into 0.5, and minus 12 will come to this joint. Same will apply for this, and same will apply for this. We will keep doing this until the values reach almost 0. So we will stop at this stage. Once we reach almost the value 0 everywhere, we will add all the values in here and will obtain the final moments. As you can see, the final moments are obtained by adding the values in here. Once these values are obtained, next we are going to draw the bending moment diagram of the structure. To start with drawing the bending moment diagram, first of all, we'll draw the length of the beam. Then, since we know the values at the joints, we'll write down those values. At point A, we had 62.5 kilonewton per meter. We had the value for point B, we had the value for point C, and we had the value for point D. Next step is to connect them using different types of lines. Since there was no load from point A up to point B, so this will be a straight line connecting these 2 points. Some here in middle, the value of the moment will be 0. From point B to point C, we had a uniformly distributed load. So the moment diagram at this portion will take a curved shape. So it will be something like this. The main thing in here is to obtain the value in here. What will be the positive moment in here? Let's calculate that moment. As you can see, we have separated the portion BC from all of the structure. We know the final moments on both of the ends. Besides that, we have a distributed load. The first thing in here will be to obtain the values of shear at point B and shear force at point C. For this purpose, we will use the equilibrium equation for moment. The total moments at point B will be 0. We have 125.2, which is in counterclockwise direction and will be assumed as positive. For this load, we will multiply it by the length, which is 12. In the moment arm will be half of the length, which is 6. Then we have this moment in here, which is in clockwise direction. That's why the sign is assumed to be negative. And for the last part, we have the shear at point C multiplied by its moment arm, which is 12 meters. From here, we can obtain the shear at point C, which is 133 kilonewtons. Since we know the summation of the vertical forces will be 0, so in here we can obtain the shear at point B as 107 kilonewtons. Once these values are obtained, we know that somewhere in the middle here, the shear force will be 0. And that's where the moment will be maximum. In order to obtain that point where the shear will be 0, we'll take a section of this. The length will be assumed as x. In here, we'll write down 107 kilonewton, which is VB, minus 20 kilonewton per meter times x. This will equal to 0. From here, we can obtain the value of x. So again, using the equilibrium equations, if we take the summation of the moments around point B, we can write down this moment, which is in counterclockwise direction, and it's assumed as positive. The moment generated by this force, which will be negative since it will go in clockwise direction. And again, at this distance, we will have another moment which we don't know. That will be written down as m. The moment m will be 161 kilonewton times meter. So the moment will be 161 kilonewton times meter. Next, since we had a point load in here, the moment line should go this way. In order to obtain the value in here, we can use the same method that we applied for this. That moment will be obtained as 242 kilonewton times meter. Again, the moment will come down to minus 234 kilonewton times meter. In order to complete our moment diagram, we will connect these and the moment diagram will be completed. So this is how you can perform moment distribution method for indeterminate beams in structural analysis. If you have liked the content of the video, consider subscribing to the YouTube channel and following us on Instagram and LinkedIn. Thank you very much for watching.